ANSYS Simulation, Lecture 8, Part 2, Transient Thermal Analysis. And we'll drag the transient thermal procedure and drop it on the geometry. And this is the first part of this lecture, a steady state thermal analysis. And we'll implement transient thermal analysis. So first of all, I'll add a aluminum alloy material to this project and go back to project schematic, and then enter ANSYS mechanical. And the first step is to connect the material with the geometry. So now we are in ANSYS mechanical, and I'll choose the geometry and link it or connect it to the aluminum alloy. So I have finished with the first step, geometry, and the second step, material. And the third step will be generating mesh or build the mesh. And this is the mesh. For step 4, keep in mind that this is transient thermal analysis. So the initial temperature is important. I'll make it 25 degrees Celsius. And also, the analysis setting, the time step is also important. The number of step is 1 step, but the end time will be, step end time will be 2,400 seconds. And for the stepping, I'll choose off, and I'll make it a sub-step with a sub-step of 80 sub-steps. Number of sub-step, or I can define the sub-step in terms of time. For example, 60 seconds per step. They are equally fine. So this is also important, especially for transient thermal analysis. In other words, for transient thermal analysis, the initial temperature is important, and also the time step, the beginning time and the end time, and also the time step are all important. So now I'll add the heat source on the bottom surface at 28 watts. And also I'll add convection heat transfer on all surfaces except for the bottom surface. And the convection heat transfer coefficient will be 10. And this is in SI unit. The unit is very important. And the ambient temperature or the room temperature will be 25 degrees. And this is also very important, that the convection coefficient of stagnant air is 10. So this is a convection coefficient for still air. The air does not move, a stagnant air. So now I can go ahead and implement the solution. So I can choose the result to be temperature result and calculate. And this is step 5. For step 6, this is the result. So now I'll tap or probe this point, which is the same spot as the steady state solution. And now I'll make it a curve. So this is the result, right? I probe the result of the spot, and I'll display the graph of the data, and the green one will be the lowest temperature. The green one will be highest temperature, higher temperature, and the red one or low temperature. It is a little bit misleading, right? But the low temperature will be red one. So we can see here that the temperature goes to about 100 degrees, 126 degrees. So I can probe this number, and this is the result that I probe, right? So I I'll display the result of this probe spot. Okay. Now, this is the temperature that I have tapped, and beware that in the steady state thermal analysis, the final temperature is also 120 degrees C. So that means that the system will be heated and the temperature of the spot increase from 25 degrees at time 0 to about 1,800 seconds, where it reaches a thermal equilibrium, and it actually becomes a steady state condition from here on. So when the time gets to about 1,800 seconds, the system reach a thermal equilibrium condition, and actually this situation will be the same as that in steady state thermal analysis.